Our next presenter is actually taking robots to new heights. He's created swarms of agile aerial robots which aid in search and rescue. He's the UPS Foundation Professor at the University of Pennsylvania. Please join me and give a big SOLIDWORKS welcome to Professor Vijay Kumar. Vijay? Thanks for joining us.
Good morning. It's a great pleasure to be here at this conference to tell you about some of the work my students and I are doing in building aerial robots like this. Actually, Rob Herman told you the difference between people who make things happen and people who watch things happen. My students make things happen, I watch them happen. So the robots we build and design are closely related to unmanned aerial vehicles that you see here. But there's 2 or 3 big differences. So these vehicles are not really robots. They're remotely piloted, oftentimes by a crew consisting of many, many operators. They're pilots, they're sensor operators, they're analysts, they're mission coordinators. And these UAVs are big. They weigh thousands of pounds. In contrast, the robots we try to build are something that you can carry in your arms. At most, 1 meter in diameter, at most, a couple of kilos in weight, and they fly indoors. The smallest one that you see here on the top actually weighs a little less than 75 grams. All these robots on the left side are called quadrotors, and that's because they're helicopters with 4 rotors. So you can imagine if you rotate all motors at some nominal speed, then the lift generated by these rotors compensate for the weight and the robot hovers. On the other hand, if you carefully control these speeds, you can get this robot to roll, pitch, and yaw, and fly in whatever direction you want. The smallest robot that we have, as I said before, weighs a little less than 75 grams, is about 21 centimeters in diameter, and consumes between 10 to 15 watts of power. So robots like this can be used for emergency response applications. Imagine a 911 call in a building like this, and the first responders on the scene are robots. They gather information and provide this information for human rescue workers that might come much later. They can also be used for search and rescue, as you see here. So these are pictures of our robots in Sendai when we did experiments following the earthquake in July 2011. And you can see here the ability of these robots to fly in collapsed buildings and take pictures and send information back again to human rescue workers. You can also use these robots for construction and for transportation. So in the video on the top left, you see robots assembling truss-like elements with magnetic rods forming 3-dimensional structures. This is only a laboratory prototype, but you can imagine bigger robots performing construction tasks on a larger scale. Or even smaller robots, as you see on the bottom right. If you build smaller robots, the payload's going to be smaller. Well, you can get these robots to collaborate to pick up larger payloads. Size does matter. So if you take the characteristic length R of a robot, now I'm allowed to use mathematical symbols here since we're all geeks here. We know that the lift scales as the square of this length. But what also helps us is that the inertia also scales as powers of R. So if you make R smaller, let's say by a factor of 2, the lift drops by a factor of 4, but the mass also drops by a factor of 8, and in fact, the inertia drops by a factor of 32. So when you try to compute the acceleration that you get from scaling down, the linear acceleration actually increases. It goes as 1 over r, and the angular acceleration even more so. It goes as 1 over r squared. So you get 4 times the angular acceleration as you scale down the length by a factor of 2. So this works to our advantage. As we build smaller and smaller robots, those robots become more agile. So what you see in this video is one of our smallest robots doing flips, double flips, the single flip can be performed in half a second, and the robot accelerates from hover position to a maximum angular speed of 2,000 degrees per second in less than 1/4 of a second. So again, all this is possible because an onboard computer carefully monitors signals from an onboard gyro and accelerometers to stabilize the aircraft to hover. So one of the co-inventors, Daniel Mellinger, throws this robot into the air, and you can see this robot recover no matter what position it's in and return back to him safely. So we want to take robots like this and make them autonomous. So a key issue you really have to deal with is motion planning or path planning. In other words, how do you get from point A to point B? So here's a schematic. On the right side, you see what I've tried to draw here, which is a 12-dimensional picture, which I can't really draw. But what I want to convey to you is this idea that if you look at the dynamics of a robot like this, it's complicated, can be only described in a 12-dimensional space, and further, this space is curved. And the reason it's curved is when you write down the equations of motion, they have all kinds of nonlinearities. What we have to do is plan motions for this in real time. So if you consider the problem of going from point A to point B, and you want to perform all these computations on onboard processors, this is quite hard. So there's a trick that allows us to transform this 12-dimensional space into a flat 4-dimensional space. And in that 4-dimensional space, all you have to worry about is the position x, y, and z, and then the yaw angle. If you can find sufficiently smooth trajectories in this 4-dimensional space, trajectories that avoid obstacles, then it's possible to take that and transform it back to the 12-dimensional space. And this is the trick that our robots use to plan motions in real time. So what I want to show you is some examples of experiments that we have done using this strategy. In the first video you will see is this robot going from point A to point B through an intermediate waypoint C. And here you'll see that the trajectory that's planned is an aggressive trajectory. It starts from a hover position, and you can see the rolling followed by the pitching, which it has to do to stop. Again, in this flat space, it's pretty easy to find these trajectories, but when you transform it back, you get trajectories like this. And this is done autonomously. The feedback is obtained from a motion capture system overhead that provides real-time information 100 times a second. But this planning is done at 20 hertz. So 20 times a second, you can calculate these minimum snap trajectories, which are smooth trajectories that minimize the fourth degree, the fourth derivative of position to find the right paths. Another thing you can do is have them go through obstacles. So in this case, the robot knows precisely where the obstacles are because of the motion capture system, and it plans paths through these obstacles with remarkable precision. And it doesn't matter if these obstacles are moving. As long as it can predict the motion of the obstacle, the robot can plan paths through these obstacles, again, in real time. It gives you a new appreciation of the phrase jumping through hoops, doesn't it? I want to show you another clip where the robot is confronted with a window that's only 3 inches wider than the robot's height. So what you have to do here is take examples of trajectories that you've learned before and sort of stitch them together. So I want you to compare this exercise to what an Olympic diver, for example, has to do when she jumps off a springboard to gain energy and then twists her body into the somersault and then recovers gracefully. And so what this robot does is it starts from a hover position, and then it twists its body to go through this window, and then it recovers. And again, there are these 3 distinct phases that are integrated together, building up momentum, changing orientation, reversing orientation, and then switching back to hover. So again, these trajectories are stitched seamlessly in real time in response to obstacles that are confronted. So I want to switch gears a little bit and talk about one of the limitations of scaling down, which is really this issue of size. And what we really want to do is get lots and lots of robots to collaborate if you want to carry payloads. Now, these payloads might be objects that you want to transport, or sensors that you might want to use to map the environment. And cooperation is a fundamental aspect of all of this. And here we've been working with biologists, and this is a video shot by my collaborator Stephen Pratt at Arizona State. Nature offers several examples where groups accomplish tasks that individuals cannot accomplish. So what you see here is a piece of fig that the ants are transporting back to the nest. And if you look at this video, it's quite clear that there's no central ant who's calling the shots, right? The ants do signal each other if they're close to each other, but no ant actually knows how many ants are part of this group. All the coordination is very local. And these examples are not limited just to ants. There are certainly other examples. For example, here you see photographs of 1 million starlings flying in from all over Europe, assembling in Denmark to form these incredible formations. And again, there are 3 things that I'll submit to you that are similar to ants, these birds, and to our robots if we have to make them cooperate. First, they operate just based on local information. It is not possible. There are 4,500 people here. I guarantee you that the person at this extreme doesn't know what the person at the other extreme is doing. So you have to act based on local information. Secondly, you have to act independently. There's no one who's going to tell you exactly what to do in order to accomplish this cooperative task. And then finally, there's got to be this notion of anonymity. What I mean by that is an individual has to be agnostic to who her neighbor is. That's very important if you want to perform a collaborative task. So the ants have no identities. The robots don't care which robot is next to each other. So I want to show you a video that we've just created. This was about 6 months ago, which shows the biggest indoor swarm that we've managed to create. So these are these really small robots that I told you about. There are 20 of these flying in formation. They're all aware of their neighbors. They all solve this problem of going from A to B, but they're told by the human operator to create these formations. And these robots create these formations in a safe way, keeping track of their neighbors. These formations can be 2-dimensional, 3-dimensional. They can change dynamically to go through obstacles. And again, the control has to be very, very precise, as you see in this video, where they traverse a figure-8 pattern. And these robots come within inches of each other, and you can imagine the level of precision that's required because they're buffeted by the aerodynamics of their neighboring vehicles because of the downwash from the rotors. So this is an example where the robots are just creating formations. It makes for a cool video. But what we'd really like to do is to get them to collaborate to carry objects. And so here you see teams of 4 robots carrying payloads that individuals simply could not have carried. Now here there's a disadvantage. You can see if you group many robots together and have them carry one big payload, the overall inertia of the system actually increases and the maneuverability decreases. But what you gain here is, again, the ability to carry larger payloads. And so here you see these robots actually collaborating on identifying a piece of a 2x4 and then figuring out how to grasp it. And these are grippers made out of composites with inlaid fish hooks, which allow you to sort of dig into these 2x4s to pick it up, and they're able to move. The next example I want to show you is an example of construction. So here there are 3 robots that are assembling structures based on blueprints that look roughly like what you see in a Lego instruction booklet. So the robots are told what the pattern needs to look like, the 3-dimensional structure. The robots decide which robot is going to pick up what part and assemble it where. And here you see, fast forward, 3 experiments where the robots essentially build 3 different 3-dimensional structures. Again, the high-level specification is very simple, but the robots make all these decisions on their own in order to satisfy that high-level specification. So in all these videos, one of the things you would have noticed is this network of motion capture cameras. This makes for a very, very special piece of infrastructure. And if these robots have to leave the laboratory and go outside, it's hard to do. And so we've been working on figuring out how to get rid of that infrastructure, how to eliminate the need for that infrastructure. And here's our first attempt to do that. So this robot has two pieces of hardware. One is a laser scanner that essentially produces a 2D cloud of points at a 270-degree field of view out to about 30 meters. The second is an off-the-shelf Microsoft Kinect RGB depth camera that is, again, good to between 3 meters to 5 meters out with a 40 degrees field of view. Using both these sensors, the robot can now start distinguishing features in the environment and triangulating of those features. This allows the robot to localize, as I'll show you in this video, where the robot essentially takes off outside a building it's never seen before. It builds this map that you see on the left-hand side, which essentially is a collection of all the features that it sees. And then it's triangulating its position with respect to these features 100 times a second. So those motion capture cameras are gone, but the onboard cameras provide roughly the same information. And the reason I say roughly the same information is because these robots like this, don't have any access to a global coordinate system like GPS or our motion capture camera system. What they have to do is to triangulate with respect to features that they have located, and so they have a relative sense of how fast they're moving. But as you can see here, this robot is completely autonomous. The student who is operating this can only see the video that you see on the left, the map that you see on the left. And based on that, he can essentially command the robot to go inside a building and look for whatever information that might be relevant to the particular mission. And again, you see the camera pictures coming that the robot sees on the top right. That gives you a sense of what is actually visible to the robot, but that information is never relayed back to the human operator. The human operator only sees the robot's internal representation, which is on the bottom left. So we've used robots like this. As I told you, shortly after the earthquake, we went to Fukushima and Sendai, and this is an early experiment we did in one of the collapsed buildings. So this is in collaboration with our collaborators at Tohoku University. They created this ground robot, and the reason our robot is hitching a ride is because it's programmed to be lazy, just like humans. And the reason for that is simple. It's about the limitations of the batteries that we carry. So because we want to extend the mission life, the robot hitches a ride whenever it can. But here you can see it's confronted by this obstacle. The ground robot cannot proceed any further. It releases our aerial robot. The aerial robot goes in over this bookshelf, which is impossible for a human to actually go across, through this buckled doorway, and it's able to recover this three-dimensional information. And it integrates this three-dimensional information with information that the ground robot has, allowing this air-ground collaboration between two very different types of robots. And to just give you a quick idea of a mapping experiment we did, so this is the 7th, 8th, and what remains of the 9th floor of a building in Tohoku University in Sendai. This was, again, done 3 months after the earthquake. And you can see that the robots have collected all this information and integrated it into a map. Now, this map may not be easy for you or I to visualize, but remember that if you wanted more information, you could actually get it from the robots that have access to even more information that you see over here. So one other thing I really wanted to talk about is the ability to bring together aerial robots technology along with music and lights that really lends itself to new art forms. So this is not my work. This is not our lab's work, but my former students who have now established a company, KML Robotics, did this performance at a Saatchi & Saatchi marketing event. So what you see here is 16 of their robots coordinated with laser lights with 16 different actuators, all synchronized perfectly and choreographed to music. So art forms like this are now being enabled by a really cool mix of technology and music. And I think we'll see a lot more of this in the years to come. But next, what I really want to do is to show you the coolest video I have. And it behooves us to show it here, the coolest conference I've been to in my 50 years. This is the James Bond theme song, celebrating 50 years of James Bond. And let's watch 9 quadrotors playing the theme song, and I'm going to shut up and let you listen. So I'm at one of the largest conferences of, I think this is the largest group of talented designers, and I would be remiss in not pointing out the important role that 3D CAD design tools like SolidWorks play. We use SolidWorks for all our designs, for creating, for modeling. We model. There's more. We use it to model the frame, the motors, the boards, the processors, even the heat sinks, and then finally the cameras. And the reason we want to do this is because we're not only interested in the geometry, but we're also interested in the mass, the distribution, the inertia, and ultimately in understanding dynamic performance. We test different configurations. This one has a larger frame, a camera, and a laser rangefinder. This one is the one that I showed you, the Kinect 3D depth camera. And the cage, which is important because that's the only thing that protects our fingers. We explore 3D printed frames. We try different motors. We model details down to that little switch that you see on the bottom left. We look at accessories, whether we can actually integrate things with our quad rotors, like these grippers. And an important problem that we're working on now is autonomous charging. So what you see on the top left is an autonomous charging station. On the top right is a landing platform. And on the bottom, you see the integration with mobile platforms that eventually can allow these robots to sustain longer missions because they have an autonomous charging station on board a mobile robot that's going to support them as they move along. So model-based design tools, such as SolidWorks, play a key role, I think, in systems integration and development. But a key challenge, to me at least, is the co-design of software and hardware. So whether it be electrical hardware or mechanical hardware, we know that the value added by software is significant. And more importantly, the fraction of the value of a product that you can attribute to software is steadily increasing. This is true even in cars and airplanes, not just in robots. And in all these applications, sometimes it's hard to separate the hardware design from the software design. So I think this is a lot of challenges for people like us, at least 3 challenges. The first challenge, I think, we're already addressing, which is creating the infrastructure for innovation. That's what this conference is all about. Second, a big challenge for robotics, and certainly in all kinds of cyber-physical systems, cars, airplanes, even medical devices, is sort of this co-design of hardware and software. And third, and this may be the hardest challenge for us to address, is really making these tools widely accessible, open architecture platforms and systems. So I think this is a huge opportunity because it really changes the paradigm for innovation. Instead of having 4,500 smart, talented people here, we can now have the whole world working on these problems. And by doing this, we can lower the barrier to entry, we can increase the number of shots on goal, and truly accelerate the rate of innovation. So I think this is the big thing for us going forward in robotics. Thank you.
Vijay, thank you so much. Thank you so much. That was outstanding. I thought, you know, just the intelligence of the robots, the ability for them to work together, really just quite amazing, and really ended on a good note, I think.